This is the first technical talk of RSS. Much can and has been said about the last 18 months, but speaking personally, I find myself following news about Mars very avidly in the last year. Perhaps that's because I was seeking some sort of transcendence from the woes on this pale blue dot, but whatever the case is, I was glad to see robotic technology and the Perseverance Mars rover playing such a central role. So you can imagine how thrilled I was when Larry Matthies agreed to give the opening keynote of RSS. Larry is, of course, a well-known figure in our community. He's a senior research scientist at the NASA Jet Propulsion Lab. For many years, he was the supervisor of the computer vision group as part of the Mobility and Robotics Systems section at NASA. He is a fellow of the IEEE. He has a PhD in computer science from Carnegie Mellon University and was awarded the NASA Exceptional Achievement Medal. Thanks for agreeing to kick us off, Larry.
Hi, I'm Larry Matthies from the Jet Propulsion Laboratory, California Institute of Technology. Welcome to the conference and welcome to this presentation on robotic Mars exploration. I'd like to thank the conference organizers for inviting me to give this presentation and hope you all have a productive and enjoyable week at the conference. I've been at JPL for 32 years doing research on robotic planetary exploration and robotics for Earth applications. One of my current roles is technology coordinator for the Mars exploration program. So what I'm going to talk about today are some of the things that are new in the 2020 US Mars rover mission, in the Perseverance rover and the Ingenuity Helicopter, particularly things that I had a hand in initiating in the last 20 years. So with that, I'll move to the next slide. For those of you who aren't familiar with Mars exploration, here are some basic facts and figures. Mars is about half the diameter of Earth and twice the diameter of the Moon. It's about 1.5 times as far from the Sun as the Earth. It has about 1/3 the gravity of Earth, about 1% the atmospheric density. Temperatures range from minus 128 degrees Celsius during the polar nights to plus 27 degrees Celsius at summer at noon on the equator, and the length of a Mars day is just a little bit longer than an Earth day. So why do we want to explore Mars? NASA has these 4 themes for Mars exploration: explore for signs of ancient or current life, understand its climate, explore its geology, and prepare for eventual human exploration. Water has played an important role in all of these themes, so for roughly the decade of the 2000s, a unifying overarching theme for exploring Mars was the phrase, follow the water. We can see evidence for the role that water has played on Mars in a number of different things, including ice in the polar caps, ancient river valleys that we can see from orbital photos, and other features. This graphic illustrates missions that are operating at Mars today that were sent as far back as 2001, as well as a number of missions that are planned for the coming decade. So across the top, you see orbiter missions. Through the middle, you see landers and rovers. And then across the bottom, the bars illustrate these unifying themes I was talking about. So for roughly the decade of the 2000s, that theme was follow the water. And so we had missions on the surface that were looking to understand and show conclusively the roles that water had played in Mars geology. And we found water ice in the shallow subsurface at mid-latitudes and so forth. So once that had been achieved, the theme changed to explore habitability. We know that the surface of Mars today is inhospitable because it's too cold and has too much radiation. But the question was, with all that evidence of ancient water, could it have been habitable by microbial life? So that was really the mission of the Curiosity rover, which is still operating, and it found clear evidence that the environment could have been habitable. So now the theme has changed to seek signs of life, that is ancient life. So that's the mission of the Perseverance rover in the 2020 rover mission. It has an instrument suite designed to look for chemical signatures of ancient life in rocks. And it also has an important mission to acquire samples of rocks and soils, store those in small hermetically sealed sample tubes, and leave them on the surface. And then the plan is that the US and Europe will collaborate on a set of missions later this decade that will go and bring those samples back to Earth. I'll talk more later about how that is planned to operate. This graphic illustrates a bunch of other missions that have been sent by the U.S. and other nations. I won't talk about those today. Here's a family photo illustrating the 3 different size classes of rovers we've sent to Mars. The Sojourner rover, launched in 1996, was 11 kilograms. It was solar powered. It had an 8-bit microprocessor with a 2 megahertz clock rate, had no floating point. Then Spirit and Opportunity were rovers sent at almost the same time in 2003. They were each 174 kilograms, also solar powered. They had a higher performance processor called the RAD 6000 with a 20 megahertz clock rate, but that processor still had no L2 cache and no floating point. And then we have Curiosity and Perseverance, which are very similar in size and design with different instrument suites. Curiosity was launched in 2011, Perseverance in 2020. Both about 1,000 kilograms, powered by what we call a radioisotope thermal generator, which uses plutonium to generate heat, which is converted to electricity. They have a processor called the RAD 750, which is based on an early PowerPC 750 instruction set. The Perseverance has 132 megahertz clock rate. And in Perseverance, a new feature is a coprocessor that uses an FPGA to accelerate the computer vision algorithms for visual odometry and stereo vision so that we can drive much faster and accomplish more science in the same amount of time. Here's a partial list of things that are new in the 2020 mission. As I just mentioned, Perseverance has a new and more extensive instrument suite to search for signs of ancient microbial life in the rocks and soils on Mars. It has a sophisticated sample acquisition and caching subsystem as the first step toward eventual sample return. In order to have the best chance of finding preserved signs of ancient life, we picked a landing site that required more precise landing than ever before, as well as a terrain relative navigation system that can estimate where the spacecraft is during descent quite accurately, and then do a propulsive divert to avoid landing hazards that were mapped previously from orbit. As I mentioned, the rover needed to be able to cover much more ground in the same amount of time than previously, and that's enabled by several innovations, including the FPGA coprocessor, a smarter path planning algorithm, and some other things I'll mention later. And then, of course, we have the Ingenuity Helicopter, which is a technology demonstration to show for the first time that rotorcraft can fly on another planet. My own involvement in this mission was in conception and early work of some of the aspects of the last 3 bullets. Here's an illustration of the scientific instruments on Perseverance. Going clockwise, starting from the left, we have RIMFAX, which is a ground-penetrating radar, which probes the subsurface structure down to about a depth of 10 meters with a vertical resolution of about 10 centimeters. Mastcam Z is a stereo camera pair on a pan-tilt mast that have zoom lenses for doing 3D perception of scientific targets at long range. SuperCam is a laser-based spectrometer that has a high-power pulsed laser to vaporize little bits of rock at ranges up to 7 meters and then observe those with spectrometers to infer the makeup of the rocks. META is a weather station. On the arm, we have an ultraviolet spectrometer called Sherlock for inferring the mineral composition of rocks. It includes a microscopic camera called Watson. Pixel is an X-ray lithography instrument that measures the elemental makeup of rocks. That turret on the arm also has a rotary percussive core drill with a set of exchangeable bits, including an abrasion tool for basically grinding off the outer weathering rind on rocks. MOXIE is a technology demonstration of a device that can create oxygen from carbon dioxide in the atmosphere of Mars, and that would be useful for future human missions to Mars. The total mass of all of the instruments is 59 kilograms, and the mass of everything on the turret on the arm is 40 kilograms, so that required a very stiff robot arm. All right, so now we have a video of how sample acquisition and caching is done. This is described in more detail in the paper by Robert Moeller that's listed over on the left. So we extend the arm, place the core drill down on the surface. It can acquire core samples that are about 13 millimeters in diameter and up to about 7 centimeters long. That material is stored in a sample tube. We then bring that sample tube back to the front of the rover. Inside the front of the rover is a complex mechanism that goes through several steps. So it measures how much material is in the sample tube. It takes a set of documentation images of what's in the sample tube. Then it hermetically seals the sample tube. That has two purposes. One is to preserve the sample in its pristine condition, as well as it's part of what we call planetary protection. There's very, very low likelihood that there's biological material on the surface of Mars that could contaminate Earth, but we go to great lengths to make sure that there's no chance of that contamination. And then the tubes are stored on board. We can store up to about 37 tubes. The plan is that we will drop about half of those on the surface somewhere along the way in the rover mission. And then later on, when we send a sample retrieval mission, there will be a rover on that lander that comes and picks up those samples, brings them back to the sample return lander. And then as a contingency, we keep about half of the samples on Perseverance itself, so that if it is still operating when the sample return lander comes, it can bring those samples to the sample return lander as a way to mitigate risk. The landing site for Perseverance is Jezero Crater. You can read more about that in many places, including Nick Meingold's paper cited here. On the left, you see a false color elevation map of the crater. It's about 45 kilometers in diameter. If you look closely, you can see an ancient river channel coming in on the left side of the image. Most of the images in this presentation are oriented with north up, so this is on the west side of the crater. There's a second inlet channel on the top, just off center, and then kind of in the upper right corner, there's an outlet channel, and we can tell from the relative elevations that there had to have been a lake in this crater that was on the order of 500 meters deep. The formation of the crater has been estimated as being at least 3.6 billion years ago, and then this lake is believed to have existed somewhere on the order of 3.5 billion years ago. Looking back over on the left, if you look closely, or maybe better yet, in this close-up image or closer-up image, there is an ancient delta that formed in standing water. And so the belief is that if there were organic materials and signs of ancient life, either in the river waters coming into this lake or in the lake itself, they may be preserved in sediments in the delta. So we wanted to land there. This arrow basically shows the vantage point of this 3D rendering, which is taken from, obviously, from an elevated vantage point looking at the delta. And then you can see a strip trailing off to the upper left corner of that image, which is the inlet channel. And then these two X's on the two lower images illustrate approximately where we landed. One key advance we've been making ever since the Pathfinder mission is improving the precision of landing. So the graphic on the left illustrates the 3 sigma landing error ellipses for most of the missions since Pathfinder. Pathfinder having about a 200 kilometer long landing ellipse, all the way down to Perseverance, which was only 7.7 kilometers long. So a number of things that have made that improvement. The big jump from order of 100 kilometers down to 25 kilometers between Phoenix, Insight to Curiosity was made by something we call guided entry. So the entry phase is the part from when you first hit the atmosphere while you've still got the heat shield before you release the parachute. So guided entry is where you have an off-center center of gravity, illustrated in the upper right there. And in this case, we have a set of small rockets in the back of the aeroshell that can roll the spacecraft around the forward velocity vector. And so that steers the lift vector. We also have a navigation grade IMU inside the aeroshell that lets us detect errors in the trajectory, and by steering that lift vector we can reduce those errors, and that got that landing air ellipse down from order of 100 kilometers to 25 kilometers in Curiosity. And then the further reduction in error to Perseverance was achieved by improved timing of parachute release. This shows the Perseverance landing ellipse overlaid on a landing hazard map where color codes safety of landing, with blue being most safe and red being least safe. So you can see that a fairly high percentage of this landing ellipse is not safe to land. Where we get this map from is orbital imagery, which we have at 30 centimeters per pixel. And we have that in stereo, so we can convert that into elevation maps with a spatial resolution of about 1 meter per pixel. So with that data, we can detect all rocks with diameters greater than 1 to 1.5 meters, and we can determine slope maps. And from that, we come up with essentially a probability of safe landing at each pixel in the map. And so we then use that for this terrain relative navigation capability that in real time during the last 4 kilometers of descent estimates where the spacecraft is relative to the map with an error less than about 40 meters, and then generates a hazard avoidance trajectory and does a propulsive divert to land in a known safe place in the map. Here the graphic on the left illustrates how the terrain relative navigation process works. There is a radar altimeter velocimeter that locks up at about 7 to 8 kilometers altitude. Then between 3 and 4 kilometers altitude, a descent camera takes a series of pictures. We have map data that is derived from this 30 centimeter per pixel orbital imagery. We don't need it at that high resolution for this, so we reduce it down to, we've got a fine map at 6 meters per pixel and a coarse map at 12 meters per pixel. In real time on board, we register the descent imagery to that map. That's aided by a navigation grade IMU and by the altimeter. You can read more about all those algorithms in Andrew Johnson's paper that's cited over there on the right. So once we've got our position estimate, we compute the divert trajectory, do the propulsive divert. The spacecraft levels out at between 1 to 200 meters above the ground, and then slowly descends, and then close to the surface comes to an approximate hover and lowers the rover down on a set of cables, and we call that the sky crane. Once the rover touches down, the cables are cut and the propulsion system flies away and crashes. Over on the right, we illustrate the computer system, the coprocessor that does all that computing. So that uses a Vertex 5 FPGA to do all of the image processing. Once the rover starts operating, we use the same coprocessor to accelerate the visual odometry and stereo vision for the rover for fast traverse. You can read more about that rover traverse part of the FPGA implementation in Tom Howard's paper. So once we got on the ground, here's what we saw. The blue dot on the map here is where the rover landed, and the white line segments illustrate approximately the field of view in this panorama, which was created from Mastcam Z imagery. So if you looked on the left side of the panorama, you see a knob, which I want to relate that to the orbital image. So that knob is a bump you see near the lower line segment. And then if you look over on the right side of the panorama, you can associate that with essentially the eastern side of the delta in the orbital image. And then here we have a close-up of that knob on the left that was acquired with the Mastcam Z. If you look closely, you'll see that there's a 10-meter scale bar, which indicates that that delta height must be something like 50 meters high. Here, the little white dot on the right side of the slide showed where we landed. This graphic includes some place names for a small crater on the delta and for the river channel that comes into Jezero Crater on the west side. The terrain immediately to the west of where we landed, which is left of the landing site in this image, is not traversable by the rover. So the blue and the purple trajectories here show potential routes around that terrain. And then the mission for the rover will be to make measurements and pick up some samples on the way to the delta, drive up on the delta, take more samples and measurements, and then eventually exit Jezero Crater to the west and keep it going toward the southwest, where there is even older terrain, where we can see that there are large networks of cracks in the terrain that have been filled with cemented material from groundwater. So these are essentially ancient aquifers, and they might have housed groundwater chemistry that could have evidence of ancient life. Now I'm going to talk a little bit about how the rover navigates. This slide illustrates all of the cameras on the rover. For navigation, I only need to talk about the nav cams, which are a stereo pair on the mast with a field of view of about 90 degrees. Those are used for intermediate range 3D perception and elevation mapping to have a map for path planning. And then the HAZ cams, which is a stereo pair mounted low on the front and low on the rear. Those are a very wide field of view cameras to do mapping in the first few meters in front and behind the camera, behind the rover, I mean. Any of these stereo pairs can be used for visual odometry as well as 3D perception. The biggest new challenge for autonomous navigation in this mission was that to get all of the science done in the time available, we have to do much more driving in less time than in previous missions. So accomplishing that involved several innovations. The first is the FPGA coprocessor I've already talked about to accelerate stereo vision and visual odometry. In Curiosity, those take a few tens of seconds together. In the FPGA, it's sub-second to perform those for each perception cycle. In previous missions, we've had a stop-and-go driving mode where while we're stationary, we acquire images, do stereo vision, create the elevation maps, do the path planning, and then we drive a short path segment that's a half to one rover body length long, and then we stop, do all the image acquisition and thinking again, and drive the next path segment. So Perseverance is the first time we're doing thinking while driving, where we don't have to stop to acquire the images and generate the map and generate the next segment of path. We also have a more sophisticated path planner, so in past missions, the path planner drove around almost all of the rocks. Here we could tell from simulations that if we did that, we wouldn't make enough progress, so we had to be able to straddle rocks. So the new path planner does that. Also now with real-time visual odometry, we can correct for slip as we go, and so the path planner doesn't have to be so conservative in growing obstacles with increasing distance. The net effect of these innovations is that Perseverance can drive on the order of 200 meters per day in 3 to 4 Earth hours with what we call full autonomy, so that's with visual odometry and obstacle avoidance. And that compares to the capability on Curiosity that could only drive about 15 meters per day with full autonomy. One of the things we still can't do is explicitly recognize and reason about drifts. So the graphic in the lower right illustrates those drifts. Those are all the linear features you see there. For scale, the line segment in the middle of the flight zone is about 50 meters long. So drifts like this are ubiquitous on Mars, and we do not have the onboard terrain classification capability yet, or ability to reason about terra mechanics to decide how to drive most effectively through that kind of terrain. This slide illustrates the new path planning capability. On the left is a graphic that just illustrates the idea of straddling rocks. We have a global path planner based on D-Star that uses the 1 meter resolution elevation maps to plan routes on a 200 by 200 regional map, essentially. These rovers all do not have the ability to do simultaneous steering and drive. So what we do is we turn the steering actuators to some fixed orientation, and then we drive a path segment which is a half to one rover body long, and then we stop and return the steering actuators and drive on another fixed curvature steering arc. So that leads us to a tree-based planner illustrated in the center, and along candidate trajectories through that tree, we sample positions every 25 centimeters, and then we check for obstacles with something called an approximate clearance estimation algorithm that checks for obstacles in front of wheels and checks for high centering, and this is how we are able to straddle rocks. You can read more about the details of this in Keihatsu's paper cited over on the left. Now I'll talk for a while about the Ingenuity Helicopter. The idea to develop this originated in 2013 when JPL director Dr. Charles Alachi visited my lab and saw work we were doing on autonomy for drones for the Army and asked if we could do that on Mars. I was aware of work in the early 2000s at places like NASA Ames, the University of Maryland, and Stanford on rotorcraft for Mars, and my JPL colleague Bob Ballaram had collaborated a little bit with Stanford on that. So I told him yes, I thought we could. That led to forming a team with JPL, people from NASA Ames, AeroVironment, University of Maryland, University of Minnesota, and NASA Langley to develop this. The graphic on the left illustrates the main components. I won't read all the pieces, or read all the labels, I should say. You can read more about this in Bob's paper. The graphics on the left illustrate the avionics that are inside that gold rectangle underneath the rotors. So we have a set of 5 circuit cards. Inside the circuit cards, there's a battery assembly. Sensors include an optical altimeter. That's the gray structure in the lower right. It's basically a rangefinder that we use as an altimeter. It has a maximum range on Mars of somewhere like 15 meters, so we limit the altitude of the helicopter to 10 meters. The 2 little black cubes are cell phone cameras, so the downward-looking one is a global shutter VGA camera. The forward-looking one is a higher resolution rolling shutter color camera. And then we have a MEMS IMU for use in flight, and a lower drift, higher accuracy inclinometer to initialize the navigation filter before each flight. So this illustrates the avionics architecture. It has a 2-level computer architecture that's fairly typical of drones. There's a high-performance navigation computer that runs Linux, so it's non-real-time. And then there's a lower-performance hard real-time flight control. The navigation computer is a Snapdragon 801 smartphone system-on-a-chip processor. The flight computer is a Texas Instruments Hercules processor, where each one has 2 copies of an ARM R5. They're operated in dual lockstep mode, so they're processing the same instruction at the same time, and the results are checked for quality, and if they're not equal, then an error bit is flagged. We have 2 copies of that chip, so that one is a hot spare. If we get an error in one of the self-checking pairs, we switch over to the other. There's a rad-hard FPGA that has interfaces to all of the sensors and controls, and it routes data between the navigation computer and the flight computer, and it maintains state in case we have to switch back and forth between the primary and the spare flight computer. The navigation camera, of course, goes into the navigation computer. Ingenuity does state estimation with a combination of visual feature tracking, inertial measurements, and the altimeter. To keep the computational complexity and runtime of this low, we made the simplifying assumption that we're flying over a smooth level ground plane so that we don't have to separately represent the range to each feature. We establish what we call a base frame, where we select features with the fast feature detector, and then each new image after that is called a search image. We use a 3-level image pyramid with the KLT tracker to track features between the base frame and the current search image. Since we will gradually lose features, periodically we establish a new base frame where we pick all new features, and right now we do that about every 10 frames. To illustrate that, the movie on the left shows results using a testbed aircraft flying outside of JPL. So the raw image is on the left, and you see the feature tracks on the right. This has worked pretty well on Mars. You can read about the feature tracking and state estimation algorithm in David Bayard's paper. We originally had plans to do autonomous onboard landing, hazard detection and avoidance using onboard dense structure for motion. We had to delete that for cost reasons, so for each new landing site for Ingenuity, people look at images taken by the rover or taken from orbit and set a waypoint in terrain that humans determine is safe to land in. The flight control system is described in Havard Grip's paper. The helicopter got to Mars on the underside of the rover, as you can see pictured here on the left. The mission plan was that one of the first things that the rover would do would be to drop off the helicopter. And then since the helicopter itself can't find safe places to land, the rover had to go off and scout a safe flight corridor for our technology demonstration helicopter flights. Fortunately, we found that very close to the rover landing site, as you can see on the right here. For scale, the line segment drawn on the image in the middle of the flight zone is 50 meters long. Here's a log of all of the flights to date, together with some video clips from Mars showing the helicopter in operation. So in the upper left, you see some early spin tests of the rotors. In the upper right, you see the first flight of the helicopter where we ascended to 3-meter altitude, hovered in place for 30 seconds, and then landed for a total flight time of 39.1 seconds. The plan was that we would do 5 flights as technology demonstration. Originally, the plan was to do only 5 flights. So in the flight log, you can see the description of those flights. We progressively went to higher altitudes, not shown, but we also increased the flight velocity. So we started out the horizontal segments at 2 meters per second, and we increased that to 5. With the success of the technology demonstration, we decided to extend the helicopter mission into what we call an operations demonstration phase, where we're showing that the helicopter is useful for the science operations of the rover. So we've now done 9 flights, with the last one, the 9th, really pushing the boundaries on total flight distance and duration, going 625 meters in the course of 166.5 seconds. We plan to keep doing this roughly every couple weeks through August. At that time, we may need to shut down so that the rover can continue its science mission unimpeded by the helicopter, but we'll see what happens. As I described earlier, Perseverance is the first step in what is intended to be a Mars sample return campaign, with later missions bringing back samples. So this graphic illustrates that, where across the bottom shows things that are happening on Earth or from Earth. Across the top shows things that are happening on Mars. On the left, the first column shows Perseverance taking off from Earth, landing on Mars. Across the top illustrates Perseverance acquiring samples and leaving them on the ground. The second column illustrates the Earth Return Orbiter. By the way, this campaign is a collaboration between NASA and the European Space Agency. So European Space Agency is the lead on the Earth Return Orbiter. And then we have the sample return or sample retrieval lander, which includes a fetch rover. So NASA is doing the lander, Europe is doing the fetch rover. The fetch rover goes out and picks up samples, brings them back to the lander. As I mentioned, optionally, if Perseverance is still operating at that time, it can bring some more samples to the lander. A Mars ascent vehicle that we call the MAV carries the samples into orbit. The ERO rendezvous with the sample canister in orbit, brings that back to Earth, and then a capsule does Earth entry and hard landing in Utah. So to visualize that, there's an artist's concept of the sample retrieval lander with a rover on top. This is notional, these are still in design. Here's a concept for the fetch rover going out to pick up sample tubes. It then brings those back to the lander, drops off the sample tubes. There's an arm on the lander that picks up the tubes again. sticks them in this sample canister. The sample canister is in the nose of the MAV that gets launched into orbit. There's the Earth Return Orbiter, ERO. There's the MAV going up into orbit with the sample canister in the nose. The ERO and the MAV match orbits. The MAV ejects the sample canister, shown there. ERO ingests that. Then for planetary protection, there's a complex robotic mechanism inside ERO that sticks the sample canister into another hermetically sealed shell, sticks that inside the Earth return vehicle. And so this is a process that we call break the chain. It assures that nothing that ever touched the surface of Mars will be exposed on Earth before it gets inside of a level 4 biohazard lab. And then finally, ERO gets back to Earth, ejects the Earth entry vehicle, which does its re-entry and landing. So the sample return campaign will bring to fruition what the vision has been for Mars exploration for at least the last 20, maybe 30 years. So it's now time to refresh that vision. That's being approached in two ways. One is through a committee called the Mars Architecture Strategy Working Group. They met for a year and presented their report last fall. In brief, they recommended 4 science themes that you see listed here. I won't read them. Each of those themes would have a set of missions that would include orbiters, landers, and potentially in situ mobility. Exactly what those will be defined gradually over the course of the next decade or more. And then NASA every decade charters the National Academy of Sciences to develop a new vision for planetary exploration in general. That's called the Planetary Science and Astrobiology Decadal Survey. They're working now to deliver a report next March to make recommendations for science objectives and candidate missions for the decade from 2023 to 2032. So we'll have to see what the Decadal Survey recommends as priorities for Mars. Now, of course, there's also interest in sending people to Mars, and that can add a new dimension and new missions with robotic precursors going to survey human landing sites and prepare them for eventual human landings. I'm going to end with one slide each on possibilities for future rover missions and future helicopter missions. For rovers, with all the activity on sample return, it's unlikely that we'll have another Mars rover mission soon, but there is a lot of interest and activity in rovers for the moon, and any advance we make in rovers for the moon may help us in future rovers for Mars. Currently, the NASA Ames Research Center and Johnson Space Flight Center are developing a lunar rover called Viper, currently expected to launch in late 2023. It will land near the South Pole, which is an intended destination for human missions, and its objective is to search for shallow subsurface water ice deposits. That's important both scientifically and as a resource for human use. Viper doesn't have a lot of onboard computing capability, so it will mostly follow waypoints designated by human operators on Earth. Then there are several science rover concepts that have been studied for the moon. One of those is a concept called Intrepid, which would land on the near side at a fairly low latitude with the goal of driving about 1,800 kilometers in about 4 Earth years to study the last 4 billion years of lunar geologic history. And to cover that amount of distance in that amount of time, it would need a very high level of autonomy so that it didn't have to stop very often for interaction with human operators on Earth. Another concept would send a more capable rover back to the South Pole to do more extensive mapping of subsurface ice deposits, including driving into several of the permanently shadowed craters. Then there have been other concepts for a rover to land on the far side and do another very long traverse, acquiring samples from different geologic units to have those brought back to Earth. and another concept that would land on the far side to deploy an antenna for a radio telescope. Of course, if there are missions, human missions to the moon, there likely would be rovers, and those might be either robotic rovers or crewed rovers that could have autonomous driving modes. For Mars, as I said, we don't have well-defined science objectives right now that we're actively working toward for rovers, but we are doing technology development with a number of possible science objectives in mind. That technology development includes enabling greater range, greater autonomy, again, so we don't have to stop as often for interactions with human operators on Earth, reaching higher latitudes, including up to the North Polar layered ice deposits, and especially anything that we can come up with to reduce the cost of rovers so that we can afford to do these kinds of missions more often. The team of JPL, NASA Ames, and AeroVironment has been working for the last 3 years on concepts for next generation Mars rotorcraft. On the left of the slide, you see a comparison between Ingenuity and the hexcopter that we envision as the next generation Mars helicopter. The rotor blades of the hexcopter are the same diameter as the rotor blades of Ingenuity, but the overall tip-to-tip diameter of the aircraft is about 4 meters. The amount of payload that it would carry, we've been studying a range, but if we chose about 5 kilograms, we think the mass of the whole aircraft would be about 30 kilograms. It would be solar powered like Ingenuity with rechargeable batteries, but an important difference is that it would have a radio that can communicate through satellites in orbit, so it wouldn't be tied to a lander or a rover for communications. This would let it traverse very long ranges in scientific missions. We think this could perform a number of important Mars science investigations. We'll be talking about those more in the future. How far it could fly in each flight depends on a lot of variables, including the elevation of the landing site, the latitude, the time of year, because that affects the amount of solar energy available, and the amount of payload we're carrying. The graph on the right is modeling performance in the region around Jezero Crater. Hover time trades off against forward flight range, so each line shows that trade-off for a different amount of payload. Thanks again for attending this presentation. I look forward to answering your questions and look forward to the opportunity to learn about your work and to hear your ideas for how we can make space exploration even more effective in the future. And I also look forward to when we can all meet again in person. So in the meantime, enjoy the conference and stay safe. Bye.
Larry is, of course, a well-known figure in our community. He's a senior research scientist at the NASA Jet Propulsion Lab. For many years, he was the supervisor of the computer vision group as part of the Mobility and Robotics Systems section at NASA. He is a fellow of the IEEE. He has a PhD in computer science from Carnegie Mellon University and was awarded the NASA Exceptional Achievement Medal. Thanks for agreeing to kick us off, Larry.